So I'll just begin by reminding you about what the Jones polynomial is. The Jones polynomial is an invariant of a knot in three-dimensional space that was discovered about 30 years ago by von Jones. And it has, from the beginning, it's been known to have many relations to statistical mechanics and mathematical physics. So today I'm going to be explaining some new twists on the relation of the Jones polynomial to mathematical physics. But I don't want to assume you're all familiar with the Jones polynomial, so I'll start with a quick definition. So for brevity, I'll explain the Jones polynomial, the vertex model, which goes back to work of Jones, Kaufman, and others in the mid-80s. So we start by projecting a knot to a two-dimensional plane, which you can think of as the plane of the screen. We pick the projection so that the knot is immersed in the plane with only simple crossings, and also so that the height function, which you can think of simply as the height on the page, has only simple maxima and minima. This should have been drawn better to make that more clear that it was true here. And then, so there are finitely many exceptional points, either crossing points and also maxima and minima. We omit all the crossings, maxima, and minima. And that decomposes the knot into finitely many pieces. We label each of those remaining pieces by symbol plus or minus. And then you introduce a variable q, and you put local factors. So for example, if there's a crossing that looks like this, with all four strands labeled by plus on each side, you give a factor of q to the fourth. And for example, with a plus crossing a minus over a plus crossing over a minus, it's minus q to the minus 1/4, and so on. There are a few I haven't drawn. They're all weighted by 0. And similarly, you include factors for creation and annihilation events.
The plus minuses are given every link after you take out all the points.
You remove all the exceptional points. So you remove 1 point for each maximum or minimum, and at a crossing you remove 2 points, 1 on each strand. And after that, the knot is divided into finitely many segments.
You give each one of them plus or minus?
Yes.
Randomly, more or less? Or
Well, you're going to sum over all possibilities. You do statistical mechanics. And then you have a local factor. So if the local picture looks like this near an exceptional point, you include a factor of q to the 1/4. If it looks like this, you include a factor of the square root of minus 1, I, times q to the minus 1/4. So you have a finite sum. You sum over all possible labelings. So for the example I drew, there would be roughly 30 exceptional points. So you remove them. You have 2 to the 30 possible labelings. You do a sum of roughly 2 to the 30 terms. And you get, obviously, a Laurent polynomial in q, or actually in q to the half. And this is known as the Jones polynomial. And its main property.
So you sum the product of those factors?
Yes, that's right. You take the product over all. Let's say there are 30 exceptional points. There are 2 to the 30 possible labelings. For each labeling, well, the number of local factors is less than 30, but you multiply all those local factors. And after you've summed all the local factors, you get a function of q, which is the Jones polynomial. Well, the way I've defined it, technically, it's actually an invariant of a frame knot, where the framing is related to the way it was projected to the plane.
Now, in the formula gives them 1/4, but this cancels to 1 I.
Yes, right, because the number of crossings has to be even. Well, sorry. Okay. Sorry. I'm oversimplifying this a little bit. If you use the what's called the canonical framing, which you won't get immediately from these formulas, then what you get is q to the 1/2 times the Laurent polynomial in q.
what's the framing?
Well, a framing is a trivialization of the normal bundle to a knot. So if you have projected the knot to the plane, then the vertical direction from the plane is a section of the normal bundle, which is a trivialization. It's not what's called the canonical framing. So there's some details about knot theory I don't really want to get into. The main idea here is that, leaving some technicalities aside, you get the Jones polynomial by this finite sum of 2 to the 30 terms. And that gives you a function of q that's miraculously independent of the projection that you picked. So that's the main, well, okay. After you know this, then you can apply it to various questions of knot theory. But the main, at least for my purposes, the main property is that the finite sum does not depend on the choice of how you project the knot to the plane.
Except this question of framing.
That's right, except for the way the framing depends on the projection. So that means up to an overall power of q, which I don't want to talk about. It doesn't depend on how you project it to the plane. So then, in the 80s, a lot of descriptions of the Jones polynomial were found, usually involving mathematical physics. So a lot of methods were used: statistical mechanics, braid group representations, quantum groups, two-dimensional conformal field theory, and probably things I'm forgetting. And one thing that was learned, notably by work of Tuccia and Kanya in two-dimensional conformal field theory, is that something like the Jones polynomial can be defined for any Lie group G and representation R. So the Jones polynomial is actually the case that the group is SU2, and R is the two-dimensional representation. In other words, the spin 1/2 representation. So you can think of actually the symbols plus and minus as the weights of the two-dimensional representation. So there's an analogous vertex model for any representation of any group. And always you would remove the exceptional points and then label the segments by the weights of the chosen representation. But, okay. And then the theory of one approach is that the theory of quantum groups can be used to determine the local factors that you need. Now, with these clues and also some advice from Atiyah, I found a description of the Jones polynomial in terms of three-dimensional gauge theory. So here we do gauge theory with the gauge group G and gauge field that I'll call A. Well, so we need to pick an action for the gauge field, and it should use no structure on a three-manifold except an orientation. Because if we, for example, use a Riemannian metric, we won't have much hope of getting a topological invariant, such as a knot invariant. So what is a gauge invariant function of a connection that we can write by integrating on a three-manifold a local expression, or on a three-manifold that has only an orientation? Well, there's only one candidate, which is the Chern-Simons function, which I define this way. This isn't the most general definition, but if our bundle is trivial, so that the connection can be represented by a one form valued in the adjoint representation, then the Chern-Simons invariant is given by this simple integral. Now, the peculiar property it has is that the integral is gauge invariant, almost, although the function that's being integrated is completely not gauge invariant. The integral is actually gauge invariant modulo 2 pi times an integer. And that's really, for today's lecture, essentially the only thing you need to know about this function. So if you haven't met the Chern-Simons function before, all you need to know about it, really, first of all, it's the only candidate for an action if we're trying to make a topologically invariant theory, and it's gauge invariant modulo 2 pi times an integer.
Do you need to explicit formulation? Because
Well,
it doesn't work for if it's not trivial and
well, what we'll need to know is that a critical point corresponds to a flat connection. That's true in general. Now, what would be called the partition function of Chern-Simons gauge theory on a three-manifold, formally, well, you take the exponential of the action, but we'll take the action, exponential of I, the square root of -1 times the action. We'll take the action to be k times the Chern-Simons function. But k has to be an integer because the Chern-Simons function is only gauge invariant modulo 2 pi times an integer. And then, formally, we consider the path integral over the integral over the space of all connections. U is the space of all connections. We integrate over all connections. We divide by the volume of the gauge group. We're just imitating quantum gauge theories as used in particle physics, except that we're in 3 dimensions instead of 4, and the action is the Chern-Simons action instead of the usual action. So this integral is defined with no structure on M except an orientation. So it's an invariant of the three-manifold M. I'm suppressing some details. If you follow the logic of renormalization theory, you'll learn that M has to be framed, which is also true for the knots. That was a detail I suppressed a little bit when we discussed the definition of the Jones polynomial. Now, if you want to include a knot, well, what's a knot?
what does frame?
Well, for a three-manifold?
Oh, so it's a tangent.
Well, you can use a little bit less, but it's sufficient to have a trivialization of the tangent bundle. The tangent bundle of a three-manifold is trivial. You pick a trivialization. If you change the trivialization, then this is multiplied by a root of unity. So it's a little bit like the knot. In that case, if you change, not a root of unity, sorry, a fractional power of q. Q to a rational power if you change the framing. Just like the fact that if you change the framing of the knot, you get an overall power of Q. Sorry, I haven't explained what Q is quite. I will in a moment. Sorry.
So do you assume physically conductivity?
Well, we can, but we don't have to. We can study.
It's not clear what K is, so all you normalize.
You normalize. K is whatever it can sensibly be. So I don't want to really describe the general theory of defining Chern-Simons. But yeah, that's correct. Yes, right. So whenever there's for any G, whenever there's an expression like this that makes sense, you try to make a quantum theory. And the non-simply connected case has interesting properties, some of which were actually first explored by Moore and Seiberger in 1990. Now, to include a knot, which means an embedded circle in M, well, we need to find some gauge invariant function of a connection that makes use of a circle, but doesn't involve any Riemannian metric or other structure. And the obvious one is to pick an irreducible representation of R. It doesn't have to be irreducible, but we might as well pick an irreducible representation. Then we define what, in this context, is called the Wilson loop operator. But the Wilson loop operator is just the trace of the holonomy. So I like to say that holonomy is a 19th century concept, but you can get your name on something in the 20th century or even the 21st century if you're the first to use it in quantum theory. So that's the Wilson loop operator. And then we define an invariant of the pair M and K, which is the same integral as before, but including a factor of the trace of the holonomy. So formally, this is only depends on the three-manifold M with the embedded knot K. And if you follow the logic of renormalization theory, you'll find out that you predict that that's actually true quantum mechanically, except that framings are needed everywhere.
So why do I need renormalization theory?
Well, in quantum theory, you need renormalization theory. So as a physicist, if you want to discuss, you can write down a formula like this, but if you want to decide if it makes sense, you have to investigate what kind of renormalization is needed to define it quantum mechanically. And that has to do, roughly speaking, with what kind of counterterms and anomalies are possible. And if you go down the standard route in this context, you'll find that the only trouble you expect is that both the three-manifold and the knot need to be framed. I could explain it, but it would be a little bit of a digression.
So you don't have, the counterterms don't play a role.
Well, the role they play is that you do not quite get a perfect topological invariant. So you don't get, you do not get the usual sort of infinities people worry about. For example, the Chern-Simons term can't be renormalized because K has to be an integer. And there aren't any other possible terms in the action given the topological invariance. The basic question you should ask is whether quantization will spoil the topological invariance. And if you follow the logic of renormalization theory, you'll find it only spoils it by C-number terms, whose
By which?
what physicists would call C-number terms. In other words, to actually quantize, you have to pick a metric. Then you ask, in the end, does the result depend on the metric? You find it only depends by C-number terms, terms that depend on the metric and not the quantum variables. So topological invariance is just marginally spoiled. The way a topologist would say it is that the three-manifold and the knot need to be framed. I mean, I could explain it in more detail, but perhaps not right now. Now, if we specialize to the case that our three-manifold is just R3, and we take G to be SU2 and R to be the two-dimensional representation, then the knot invariant we get this way turns out to be the Jones polynomial evaluated at a certain root of unity.
Before I was thinking your manifold was compact.
It can be compact, but it doesn't have to be.
Here, or you take care of infinity.
Well, if you were doing differential geometry, you probably would say that the connection goes to infinity, and you divide by gauge transformations that are 1 at infinity. And you do something like that quantum mechanically. So R3 is almost the same as S3, but if you were doing S3, you would divide by the gauge transformations that aren't necessarily 1 at infinity. So the two answers would differ by a factor of the volume of the group. That's a universal factor independent of the knot. So it's almost the same to do R3 or S3. But for what I'll get to later, it's simpler to describe if we are on R3.
So MP I can think to it as S3 plus trivialization.
Trivialization at a point, yes. So I claim that what we get this way is the Jones polynomial at a root of unity. Now, this is only a discrete set of values of Q, but of course these values are enough to determine a Laurent polynomial if you know that the answer is a Laurent polynomial. From this point of view, it's not especially obvious that the answer is a Laurent polynomial. So the argument that what you get this way agrees with the Jones polynomial and its usual generalizations to other groups and representations involves making contact with conformal field theory through the work of Tsuchiya and Kanya. And this gives a link between three-dimensional gauge theory and two-dimensional conformal field theory that has a lot of fun applications. For example, it's also important in condensed matter physics, in studies of the quantum Hall effect, and more contemporary things related to that. So gauge theories with Chern-Simons gauge group are used to describe topological order in fractional quantum Hall systems, for example. There are all kinds of things people speculate about, but the most famous example involving a material that actually exists in the lab is something called the Moore-Reed state, which is suspected to describe a certain material that people actually have in the lab, and it is believed to involve G equals SU2 and K equals 2. But, of course, condensed matter physicists hope to find other materials that will involve other values of K. So this approach gives a definition of the Jones polynomial with manifest three-dimensional symmetry, not relying on a projection to the plane. But there were at least two things that many knot theorists didn't like. One was simply that quantum field theory is difficult to understand mathematically. So physicists are quite familiar with the framework in which I presented this, but most mathematicians are not, and it's difficult to understand it mathematically. The second issue was that we did not get a direct explanation of why the Jones polynomial is a Laurent polynomial in Q, rather than just being a function of an integer variable k. Most other approaches to the Jones polynomial, like the vertex model that we started with, do not obviously give a topological invariant, but they do obviously give a Laurent polynomial. Now, for most three manifolds, the answer we get from the gauge theory is believed to be the right one. It's special to knots in R3 or S3 that the natural variable is Q rather than K. On a generic three manifold, the quantum invariants, as far as is known today, depend only on an integer K and do not have natural continuation to functions of Q without losing some of the three-dimensional symmetry. Actually, I'll explain later, sort of, well, I won't have time to completely explain it, but I'll tell you about the framework for understanding how they can be analytically continued. But on a generic three manifold, the analytic continuation is not as nice as it is on R3, for reasons that I will have time to explain.
So the variable is in fact Q1R, so I just take the exponential of R1R.
Yes, right. Well, yes. Many authors actually use Q, or what I call Q to the half is called Q by some authors, but in the presentation I'll give, this is the most natural variable. However, so the answer we get from the gauge theory is the right one for a generic three manifold. If you want to complete quantum topological invariance, K has to be an integer. But for knots in R3 are special, and the answers really are naturally Laurent polynomials in Q. And for most of the last, well, I wrote here 25 years, but I think it's, yeah, okay. For most of the last 25 years, I just accepted that that was the answer, that Chern-Simons gauge theory wasn't a good way to explain the special properties of knots in R3. And if you wanted to understand that, you had to make contact with one of the other approaches, like conformal field theory in 2 dimensions. But some things happened more recently that made me take another look. These are two developments of roughly the last decade. One is called the volume conjecture, and the other is Kovanov homology. So I'll tell you about the other look I took, but first I'm going to say a few words about the answer I arrived at. So here we're going to discuss the matter a little bit from the point of view of condensed matter physics. So, and the only gauge, but in this discussion we're going to not consider exotic materials, quantum Hall systems. So the only gauge field we're going to consider is the electromagnetic field with gauge group U1. And it has the property that it exists throughout all of space-time. We can discuss how it interacts with the material, but the line bundle and connection are defined everywhere. So we're going to consider, the way condensed matter physicists would say it, we'll consider a material that has no relevant degrees of freedom, not even topological ones. So we consider only U1 gauge theory.
So we can't get a word polynomial?
No, no. I'll tell you some fun things, but we will not discuss the Jones polynomial. We would have to consider more exotic materials to make the Jones polynomial relevant. It would be a fun lecture, but it's not the direction I'm going in today. So first we consider an abstract two-dimensional material floating in empty space. So it's anything which is much larger in 2 dimensions than in the 3rd dimension. It could be a sheet of paper, although that'll be a valid example for what I'll say, but it won't be an interesting example. Somewhat more interesting is some kind of atomic or molecular monolayer of the right kind of material. The effective action for its interaction with the electromagnetic potential, so it's a 2-dimensional material, but there's a 3-manifold if you include time. And the action describing the situation is going to be an integral over all of Minkowski space of the Maxwell action. But then there's some kind of an integral over the world volume of the material. Of what? Well, there are all kinds of local expressions. All we know in general is that the effective action is a gauge invariant local expression made from the connection. And there are all kinds of possible terms.
So these materials move as a boundary and give both magnetic field and this material.
Yes, but from what I'm about to say, you could assume its position in space-time is known. And we just consider, yes, you could consider it fixed. I won't say anything that depends on the motion.
So it's
There's a fixed 3-manifold in 4-dimensional space. The action for electromagnetism is now the action that describes Maxwell theory. We can write it differently, simply as F wedge star F. And then there's also something integrated over the world volume of the material. And that something, in general, is completely general. It could have the square of the electric field, the square of the magnetic field. Well, it could have the electric field dotted with the normal vector to the material. The material might not be rotation symmetric locally. All kind.
You have matter field there or not?
We have whatever there is. Sorry, no. We assume there are no relevant materials. So I'm writing an action, no relevant degrees of freedom in our material. The material is an insulator. So in its interaction with electromagnetism, you don't have to consider charge degrees of freedom. You just write an action for the electromagnetic field only. In general, it's a completely general 3-dimensional action with no symmetries. Its only general property is that it's gauge invariant. How can it be gauge invariant? Well, it could be the integral of a gauge invariant local density. For example, the square of the electric field. There are infinitely many such terms that are possible, and they describe all kinds of standard physical effects, polarizability, susceptibility, and so on. And all that would be the case if we had a 3-dimensional material filling part of a 4 volume. But on the boundary, if there is a boundary, there could be a funny term on the boundary. You're correct. So there are bulk interactions, but there can also be interesting boundary contributions in the action. Although I won't go far enough to tell you about them, but it's extremely interesting to do so. So there are a lot of terms that would have analogs for a fully 3-dimensional material. But there's one term that's special for a 2-dimensional material. And the reason it's special is that the integrated expression is gauge invariant, although the local density is not. Although this is only a true statement if our material has no boundary. So you should imagine our atomic monolayer has been formed into a sphere. Otherwise, we have to discuss what happens on its boundary. And if you're familiar with the Chern-Simons function, you know that it's not quite gauge invariant on a 3-manifold with boundary, so something funny would have to happen there. And that funny thing is, well, led to the Nobel Prize for quantum Hall currents. But we won't discuss it today, really. There's this one interaction that's very funny because it's only gauge invariant mod 2 pi if k is an integer. For physics, it has to be gauge invariant mod 2 pi, as we learned from Feynman and Dirac, because you have to exponentiate I times the action. So the action has to be gauge invariant mod 2 pi. And then it turns out that k is the coefficient of the Hall current. So to understand that, well, it's not hard to understand, but we wouldn't be able to get to what I want to tell you about. So this approach gives an attractive and familiar, although slightly abstract, explanation for quantization of the Hall current in any two-dimensional material that obeys our assumptions. Our assumptions were that there are no relevant degrees of freedom, not even topological ones. In other words, our assumption was that you can describe the physics completely by some kind of effective action for the electromagnetic field with no other variables. Given that, Hall currents come from this funny term in the action, and the coefficient is an integer. And, yes? Yes. Sorry, I'm not sure. You mean the material is embedded in a four manifold? But it didn't have to be conceptually. Well, I'll discuss in a moment the case where k is not an integer, does not have to be an integer, and then you can ask your question again. Let's postpone your question for a second. Well, I'll also explain that in a second. Okay. Now, okay, there's a twist on this tale that's also familiar for condensed matter physicists, at least, because of developments in the last few years involving topological insulators, which again are materials that really exist in the lab. So suppose our two-dimensional surface is not freely floating in empty space, but is the surface of a fully three-dimensional material. Then, so first of all, we'd start by saying the same thing. The action has a term which is a bulk term, and then it has a term which is an integral over the world volume of the material. But then, as Pierre was telling us, you could also have a boundary term. And now the boundary is, again, a three-manifold. So you think that the Chern-Simons function of the gauge field in the three-manifold can contribute. And it can.
So here again, this object is fixed.
Yes. I mean, for our purposes, yes. So we're scattering light from it or something, but it's much too heavy to move as a result of the interaction with the light waves. So if our two-dimensional surface is not freely floating in empty space, but is the surface of a fully three-dimensional material, any real valued k at all is possible. And before stating this physically, I'll just state the underlying mathematical fact. So suppose W is a three-manifold without boundary, and A is a U1 gauge field in W, and we'd like to define this function as a gauge-invariant real number. Well, we can't. It's only gauge-invariant mod 2 pi. But suppose we're given more information. Suppose we're given a four-manifold M whose boundary is W, and we're given an extension of A over M, with the curvature or gauge-invariant field strength being the usual thing. Then there's no problem. We replace I with I hat, which is this. That's the integral of f wedge f, written the way physicists like to write it. Well, this is manifestly gauge-invariant and well-defined as a real number. And mod 2 pi, it's congruent to I. So if we're given this additional information, we can define the Chern-Simons function as a well-defined real number. Well, usually in physics there are initial and final conditions. And if you specify initial and final conditions, it's as good as a compact manifold. Yes? Well, there's some discussion involved, but conceptually what you do eventually is you specify initial and final states, and then it, for the questions we're discussing, it behaves as if it was a compact manifold. So since I hat is completely gauge invariant, I hat is the four-dimensional integral, a term k times I hat is possible in the effective action for any real k. But since this is the same as ki mod 2 pi times k, it means that the surface of an insulating material, where we may assume that the bulk and the surface are completely gapped with no relevant degrees of freedom, can have Hall currents with an arbitrary coefficient. And moreover, this should not be an exotic effect. We should expect this effect to happen in any material that does not have a discrete symmetry that would prevent it. For a generic material, the effect might be small, but we should not expect it. I'm not even sure it should be very small, but anyway, it shouldn't be 0 unless it's forbidden by symmetry. An example of a symmetry would be a reflection symmetry. So K might be measured by scattering light from the surface, although this measurement hasn't been made yet. It's only a theoretical prediction. Now, in condensed matter physics, the most interesting variant of what I've said is probably the case of a topological insulator, which doesn't exactly fit what I've told you so far in the usual presentation. The boundary is not gapped, and there's much more to say. It's a fascinating story, which actually would be fun to talk about, but we don't have time for it today. So instead, we're going to focus on using what I've said to get inspiration about how to formulate Chern-Simons theory of the Jones polynomial to understand how to continue it away from integer k. So we end up learning much more than that, and I'll say as much as we have time for. Natty, did I answer your question by now? Yes. Because, you see, you need to know that the physics describing the material doesn't depend on how it's embedded in a four manifold. If it's the boundary of a material, then it does. But if I have an abstract surface in space, physics being local, let's say it's a very big sphere, without changing anything that's less than 1 inch from the sphere, I could cut out a hole inside and glue in something else. And without knowing what was glued in, we wouldn't be able to define Chern-Simons function except mod 2 pi.
You started by saying something much more concrete. You started off what?
Yes? Yes. When it's embedded in space-time in a particular way, we know how to fill it in. But physics being local, if you have a two-dimensional material that obeys our assumptions, it has to be described by physics that doesn't depend on the four manifold it was embedded in. You have an atomic monolayer that somehow develops a mass gap. So you have a very big sphere. It's somehow embedded in a four manifold, but the effective action describing it doesn't know how it was embedded in a four manifold. The opposite case is that it's actually the boundary of a material. Then in that case, you'd say that it can't depend on what there is in space-time outside of the material, but it can certainly depend on what's inside. Is that not sufficiently convincing?
Whether A is extendable to R4?
No, A is extendable to R4 because, after all, electromagnetism exists throughout R4. But the material, sorry to interrupt.
In the first place, because when you average all the A's cancels it out because vanishes. So how is that different?
Well, conceptually, you could have, suppose the material has a topology S2. Then you could have embedded it in a space-time which was S2 times a circle, or it lives at a point on the circle. And then you'd reach a contradiction if k was not an integer. So if you imagine this material only is living in R4, you can ask the questions that you're both asking. But if you bear in mind that your atomic monolayer could have been embedded in any four manifold, or any three manifold times time, then you'll reach the conclusion I stated. Now the difference when the guy was the boundary of the difference when we're discussing the boundary of a bulk material is that you can't embed it in S2 times a circle anymore.
Because you're sort of assuming that charge is quantized in units of B. If that is not the
Yes.
case, then k is not an integer, and on many
Yes.
materials,
Yes.
k is not an integer.
Well, I was trying to avoid many technicalities. So I said that we're discussing materials that can be described with electromagnetism only. So I said that we had no relevant degrees of freedom, even topological ones. I think it would unfortunately take another lecture to properly explain it. So, I mean, there are a lot of fun directions to go in, but we can't do them all. In fact, we can't even finish what I did plan. So we're going to go back to the Chern-Simons gauge theory of, say, SU2, if we're aiming to describe the Jones polynomial. And so we have our usual Chern-Simons action, and the integral is on a three-manifold W. If W is a bare 3 manifold, in other words, it's not given as the boundary of a 4 manifold, it has no additional structure, then K has to be an integer so that I is gauge invariant mod 2 pi. To get away from that, we don't want W to be a bare 3 manifold. We'll take W to be the boundary of a 4 manifold, and we'll assume that we are trying to define a topological quantum field theory on M, not just on W. And now, therefore, we will get answers that in general depend on the choice of M. And if there isn't a natural choice of M, then the choice of M will really matter and will break some of the symmetry. The problem is no longer to explain why K doesn't have to be an integer, but to explain how to get a topological quantum field theory on a 4 manifold with boundary. Why K isn't an integer isn't a problem because of the same identity we used already. Well, it's not really an identity. The right-hand side is a well-defined real number. The left-hand side is defined modulo 2 pi. So, well, it's an identity mod 2 pi, but the point is that the right-hand side is a better definition when it's available. So I put quotes about the word identity because the right-hand side is well-defined as a real number, the left-hand side is not. But with the help of this identity, there's no problem to get away from integer K. The problem is how to define a topological quantum field theory on a 4 manifold with boundary. Now, if we do succeed, we won't get a 3-dimensional topological quantum field theory because the choice of M will break some of the symmetry of W. So, for example, the mapping class group of W won't act on M necessarily. But knots are an exception. One can embed a knot in a 3-sphere S3 without breaking any symmetries. You can consider S3 to be the boundary of a 4-ball B4. In fact, this is true in a very strong sense because the diffeomorphism group of the 3-sphere is contractible into SO4, which acts on the 4-ball. So if we find the right 4-dimensional topological quantum field theory, we'll get a satisfactory explanation for why the Jones polynomial is not limited to integer K. The hard part is definitely to find the right 4-dimensional topological field theory, and I only have time for a few hints. First of all, the reason it's hard is we don't get anywhere if we just try to use the right-hand side of this identity as a 4-dimensional action. Although the left-hand side makes sense as an action, the left-hand side makes sense as an action for a gauge field in 3 dimensions, but for a reason I didn't tell you. The reason is that its linearization gives an elliptic differential operator modulo the gauge group. But the right-hand side does not. If you tried to use the right-hand side as an action for a 4-dimensional gauge field, it would be completely degenerate. It's true that the right-hand side doesn't use a metric on M, but it's too degenerate to give a sensible action by itself for a gauge field. And at first sight, there's no way to remove the degeneracy without adding terms that do depend on the metric. So to proceed, we need to know something about where topological quantum field theories come from. Now, in condensed matter physics, topological quantum field theory is usually relevant because the system is gauge invariant. Gosh, something went wrong in the middle of this slide. A system is gapped, which means that there's a gap in energy independent of the volume of the system between the ground state and any excited state. But in practice, it means that at big enough distances, there's nothing there. And the details of the geometry don't matter. Well, here we assume there was nothing there. We wrote a local expression that depended on the gauge field only, but we assumed there weren't any degrees of freedom we had to describe involving the material. And if a an insulator, which is, the technical term is, the expression is, the system is gapped, but what you're familiar with is that the resulting system is an insulator. If you have an insulator will lead at long distances to a topological field theory. But until relatively recently, it wasn't described that way because people assumed those topological field theories were trivial. It was discovered in the last 30 years, originally from the quantum Hall systems, that an insulator at long distances might be described by a non-trivial topological field theory. So for condensed matter physicists, topological quantum field theory comes in because the system is gapped, meaning it's an insulator. And then you find at long distances you get a topological field theory, which will be trivial for a lot of insulators, but in general not. But there's another source of topological quantum field theories where you focus on a selected class of questions in supersymmetric gauge theories. supersymmetric quantum field theories, not necessarily gauge theories. A supersymmetric quantum field theory has a certain number of fermionic charges Q alpha. So they're charges whose anti-commutators you consider rather than commutators.
What does the word
It's just an operator that acts on the Hilbert space. And in this case, if you're on Minkowski space, they commute with Hamiltonian. So I didn't write the word conserve, but they're conserved charges. They commute with Hamiltonian if we're in Minkowski space. If you take a linear combination of these charges, you get an operator whose square is typically a linear combination of the Hamiltonian and the momentum. But in the right situation, you can pick the coefficient so that Q squared is 0. In that case, you interpret Q as what algebraists would call a differential. You define a subsector of the theory in which you only consider operators that commute with Q, and you consider Q to be such an operator to be trivial if it's the commutator or anti-commutator of Q with something. Similarly, you only consider states annihilated by Q, and you consider Q of anything to be trivial. So you consider not everything, you consider only the cohomology of Q acting on both states and operators. And this procedure gives, well, I called it here a subsector, but you might better think of it as a quotient of a subsector. By restricting to Q invariant things, you get a subsector, and then by throwing away Q of anything, you get a quotient of a subsector. But out of a full physical theory, it produces something. And this something is frequently a topological field theory. The criterion essentially is that the stress tensor is trivial. The stress tensor is always Q invariant because Q is conserved, but you want the stress tensor to be trivial. And if so, you get a topological quantum field theory. So often, the behavior of a physical theory, which might be strongly coupled and hard to understand, is heavily constrained by the behavior of an associated topological field theory. And there's a converse. The properties of the physical theory might give insight about its topologically twisted version. For example, if the physical theory has a mass gap, then this has strong implications for the twisted topological field theory. An example of that, well, prior to Seiberg-Witten theory, when Seiberg-Witten theory wasn't available, I had used the fact that n equals 1 super-Yang-Mills theory has a mass gap to predict the Donaldson invariance of Kähler manifolds. And there I used the fact that there was a mass gap to make a prediction about a twisted theory. Another example is actually Giventhal's theory of enumerative geometry of symplectic manifolds whose quantum cohomology is semi-simple. The condition that the quantum cohomology is semi-simple would be described by physicists as saying that the theory has a mass gap. And then Giventhal's theory amounts to using the mass gap. Well, the way a physicist would try to interpret it, and I should say this hasn't been properly developed in the literature, a physicist would describe it by saying that Giventhal used the mass gap to develop enumerative theory, enumerative geometry of that class of symplectic manifolds.
Can I ask you what theory was Giventhal considering? What quantum field theory?
He was discussing a sigma model whose target is a symplectic manifold that has a mass gap. In his language, it had semi-simple quantum cohomology, but it means that the sigma model has a mass gap.
This means sigma model.
Now, if the sigma model has a gap, there are finitely many.
And his target was what again?
For example, CPN. His target was any symplectic manifold, like CPN or a complex Grassmannian, with the property that the sigma model has a mass gap. Or if it has a mass gap, that means it has finitely many vacua, all of which are massive, and they are the idempotents of the quantum cohomology ring. So, as a physicist, what you'd say is that at long distances, basically you live in the vacuum, but you have to sum over the possible vacua. So then you would describe your correlation functions in terms of a sum over vacua, or in other words, a sum over the idempotents of the quantum cohomology ring. In each vacuum, the theory is trivial, but trivial here means you get the enumerative geometry of a point, which means the cohomology of the moduli space of Riemann surfaces.
Well, Giventhal doesn't know that there's a gap in this theory, right? So what did he actually use?
He used the fact that the quantum cohomology was semi-simple. But a physicist would say that he used the fact that the sigma model has a gap. Okay. Okay. If I was on a desert island for a couple months, and I had the right references, because I wouldn't remember everything I had to do, I'd try to spend my time rewriting Giventhal's work from a point of view of a physicist. What I would use is the fact that the sigma model has a mass gap. I can't promise I'd be able to do it. But I mean, morally, yes, but maybe I'd have trouble with the details. Now, there were two developments, both began around the year 2000, that made me look for a reformulation of the Chern-Simons path integral that would make its analytic continuation more evident. So one was Kovanov homology, but I won't talk about that today. The other was the volume conjecture that was developed by these people, among others. And what I'll explain started by trying to understand the volume conjecture. But I want to stress I haven't succeeded in understanding the volume conjecture, and I'm not even entirely convinced it's true. But just understanding the framework for thinking about the volume conjecture led to a new point of view about the Jones polynomial, which is what I want to explain. Given this, I won't fully explain what the volume conjecture says. So to orient ourselves, we take this integral and we ask how it behaves for large k. So we think of it as an infinite dimensional version of an oscillatory integral, such as the one that defines the Airy function. This is a one-dimensional integral, an integral in the real line, of the exponential of I k times a polynomial. A quadratic polynomial would be too easy. That would be a Gaussian integral. So we take the first case beyond that, a cubic polynomial. And that leads to the Airy function. Well, we assume k and t are real, and then this integral doesn't quite converge, but with this, there's a well-known theory. With essentially any reasonable convergence factor, you get a result that doesn't depend on the details, and that gives the Airy function. If you take k to infinity for fixed t, then the Airy function vanishes exponentially due to rapid oscillations if the exponent has no real critical points. So if t is positive, you'll find that the critical points of this function are not on the real axis. And then the Airy function vanishes exponentially. But it's asymptotically a sum of oscillatory contribution from real critical points, if there are any, which is true if t is negative. Now, according to Feynman, the same is true for Feynman integrals, such as our Chern-Simons integral. The large k behavior is determined by real critical points. So we need to know what are the real critical points of the Chern-Simons function. And a short calculation shows that the variation of the Chern-Simons function is the integral of the variation of the connection times the curvature. So a critical point is the same as a flat connection. And part of the magic of this theory is that in 3 dimensions, the condition for connection to be flat is part of an elliptic complex. So modulo the gauge group, it's an elliptic differential equation, essentially. That wouldn't be true in higher dimensions. We can write an elliptic complex in which the condition, well, this is part of an elliptic complex. Oh, sorry. What I've said is wrong. Okay. Well, what I said was over. You'd have to add more stuff in higher dimensions. Okay. You'd have to add more stuff in higher dimensions in a way that means that you can define something, but it's less interesting. It's better. I think it's better if I don't try to fix what I said, which wasn't completely correct. But something very nice is true in 4 dimensions, in 3 dimensions for this equation. Yes. Yes. Well, the complex is very short. So you can make a self-dual complex with only gauge transformations and gauge fields. And so you can make a good theory with only the gauge field. I'm afraid of making a mistake if I try to say it better than that right now. So the critical points are flat connections corresponding to homomorphisms from the fundamental group to G. So the asymptotic behavior for large K is given by sum of oscillatory contributions associated to such homomorphisms. I wonder what's been missing. Whatever is missing is also missing here, so I don't remember what it was. Now, the volume conjecture arises if we specialize to knots in R3 so that K doesn't have to be an integer. And then usually people consider the case of SU2, but they let R be the n-dimensional representation of SU2, not the 2-dimensional representation. The corresponding not invariant is what people call the colored Jones polynomial. Then we take k to infinity through non-integer values with fixed k over n. A typical choice, not the most general thing, but a typical choice is to let k be a fixed complex number plus n, where n goes to infinity. So k over n approaches 1. The large n behavior turns out to now be a sum of contributions of complex critical points. So, okay, this is what one finds empirically by studying as I explained at the beginning, there are explicit formulas for the Jones polynomial and likewise for the colored Jones polynomial. By studying these formulas, you find that the large n behavior is a sum of contributions of complex critical points. A complex critical point is a critical point of the analytic continuation of the function Chern-Simons of A.
Well, it's complex because you chose the k to be complex, right?
Well, yes, roughly speaking.
But does it mean that we see the flat U2 bundle when
Yeah,
the VN2
yes, I'll explain it in a second. But actually, k0 could have been real, but not an integer. But nevertheless, complex connections come in. So we make the analytic continuation by replacing the gauge group with its complexification, replacing a G bundle by its complexification, and replacing the connection by a connection on the complexified bundle, which you can think of as a complex valued connection. Then the Chern-Simons function is analytically continued in the obvious way by writing the same formula. And now, a critical point of this analytically continued function is just a complex valued flat connection which corresponds to homomorphism to the complex Lie group. So if we're on R3, the fundamental group is trivial, but we're supposed to also include a Wilson loop operator in the n-dimensional representation. And when we take k to infinity with k of order n, this Wilson operator affects what we should mean by a critical point. A full explanation would take us too far afield, and I'll just say the answer. The right notion of a complex critical point is a homomorphism of the knot complement to the complex Lie group with the conjugacy class of the monodromy around k that depends on the ratio n over k.
So the idea is what the observable, which is the Wilson loop operator,
Yes.
is involved in the definition of what your critical point is.
Yes, that's because we take large n when also k. We could have kept n fixed as k went to infinity, and then it would not affect what we mean by a critical point. Not only we can do that, but I will do it later, except that time is, I can say I'm going to run out of time. So perhaps I should say I would have done it later. But if we take n and k to infinity together, then the Wilson operator affects what we mean by critical points. And this is the answer, although the explanation is a little bit too long to give now.
I'm a little confused. Those things are clearly weighted, and so if I want the general group, I have to take n to be a weight, and things will make sense.
Yes, we take the weight to be proportional to k.
But we identify weight and co-weight in some way.
Yes.
What's the volume of what? What's what volume can be?
Well, there's a three manifold has what's called a hyperbolic volume. If you're lucky, the knot complement actually has a hyperbolic metric with certain asymptotic behavior, and then you literally take the volume of that metric. But there's a more general definition for any three manifold. And the volume conjecture says that this limit gives the exponential of the volume times k.
But with polynomial on k is a small loop
Yes.
across k.
Yes. So monodromy around k means the monodromy on this little circle. Now, physicists know various situations in which a path integral is dominated by a complex critical point. But usually this is a complex critical point that makes an exponentially small contribution. There's a good reason for that. You're computing quantum mechanical probability amplitudes, but probabilities can't be bigger than 1. So a critical point can make an exponentially small contribution, but it can't make an exponentially big contribution. What really puzzled me about the volume conjecture is that for many knots, the dominant critical point makes an exponentially large contribution. For example, that's true if the knot complement is hyperbolic. So the colored Jones polynomial has oscillatory behavior in this limit if k0 is an integer, but it grows exponentially in this limit as soon as k0 is not an integer. Concretely, that's because the Chern-Simons function at the appropriate critical point has a negative imaginary part, so it grows exponentially for large k. Now, so there isn't really a contradiction with what I said about quantum mechanics because we're only discussing proper quantum mechanics if k naught is an integer, and then this doesn't happen. But I still wanted to understand better why it was happening. And I was puzzled for quite a while, but it turns out that you can find an ordinary integral that does the same thing. There it is. So that integral solves Bessel's equation as a function of n for any integer k. We want to think of k and n as analogs of the integer-valued parameters in Chern-Simons theory that we called by the same name. So in our model problem, k is naturally an integer, but there's no reason for n to be an integer. So the analogy isn't perfect, but it's good enough. If we take k and n to infinity with a fixed real ratio, the integral has an oscillatory behavior dominated by the critical points of the exponent, if there are any real critical points on the circle. If there aren't any real critical points on the circle, then the integral vanishes exponentially fast for large k. Now, to imitate the situation considered in the volume conjecture, we want to analytically continue away from integer values of k. But when we do that, we want to preserve Bessel's equation, because Bessel's equation is the analog of the so-called Ward identities of quantum field theory, which we would want to preserve in the Chern-Simons case. For our toy problem, this was done in the 19th century. We first set z equals e to the I theta, so we're trying to do this integral here. We're integrating over the unit circle. K is then still an integer. We want to get away from integer values while still obeying Bessel's equation. If the real part of n is positive, we can do that by switching to the following integration contour, which luckily you can still mostly see. Instead of just going around the circle, we come in from minus infinity, then we go around the circle, and then we go back. If k is an integer, the bits we've added don't cancel each other, so we haven't changed the function. But now, as long as the real part of n is positive, the integral converges, so we've analytically continued in k. The integral on the new contour converges, and it agrees with the integral in the circle if k is an integer. But when we try to prove Bessel's equation, we have to integrate by parts. But assuming the real part of n was positive, we don't have any trouble, because the integral vanishes very fast down here. So we get a continuation away from integer k, still obeying Bessel's equation. But how does the integral behave for large k and n with fixed ratio? If k is an integer and n is real, the large k behavior, as I already said, is oscillatory or exponentially damped. But as soon as k is not an integer, even if k and n are still real, the large k behavior with fixed k over n can grow exponentially for a certain range of k over n, just like for the color-Jones polynomial. This is elementary, but to fully explain it would be a little too long. So I won't fully explain it, but I'll just explain the technique you can use to analyze it, because that will show us what we should do to take a new look at the Jones polynomial. We're way over time, though, York. Can I take another 15 minutes? So we're trying, I'll describe it in general. We're trying to do an integral of this general form, the exponential of k times some polynomial. And, well, in our case, it's dz over 2 pi iz, but in general, it could be dz times a Laurent polynomial, or a rational function, maybe. But the main thing is that there's an exponential, and we're interested in taking the exponent large. So f of z is a holomorphic function, and gamma is a cycle which might not be compact, but at least it's the cycle on which the integral converges. In our example, the function is log z plus lambda times z minus z inverse, where lambda is n over k. But you see that f is not multivalued because of the logarithm. It's better to pass to a cover of the z-plane on which f becomes single-valued. So we introduce w, which is log z, and then we work with this function, which is now w plus lambda times e to the w minus e to the minus w. And now, since you can't quite see our integral, I'll just write it. Our integral is now simply the integral dw of e to the k times f of w over some cycle. Yes. So we want to discuss all possible cycles in which this integral converges. So Morse theory gives an answer to the problem of describing all possible cycles in which this integral would converge. We consider the real part of the exponent as a Morse function. Its critical points are just the critical points of the holomorphic function f. So in our example, they obey this equation. And that's a quadratic equation for e to the w, so you can find them all. And now the key step is the following. To every critical point p of h, in other words, every solution of this equation, you can define an integration cycle gamma sub p called a Lefschetz thimble on which the integral converges. For this, I'll just draw a picture. The picture looks like this. The real part of a holomorphic function doesn't have local maximum or minima. It only has saddle points. So I've tried to draw a saddle point. The function goes up in one direction and down in the other direction. And starting at a critical point, you want to flow down to define the Lefschetz thimble. So you get, well, under a technical condition that there are no flows in Morse theory from one critical point to another, which will be true for a generic function, you get a cycle for every critical point, and Morse theory tells you that this gives a basis of all the cycles in which the integral converges. So in general, you define the Lefschetz thimble by the gradient flow equation of Morse theory. You pick a complete metric on the W plane, for example, the obvious flat metric, and you write the gradient flow equation, where I've introduced a new time coordinate. And then the Lefschetz thimble is defined as the space of all values at time 0 of solutions of the gradient flow equation on the semi-infinite interval that start at the critical point at time minus infinity. For example, there's a trivial solution that sits at p for all time. So that's p itself is contained in the Lefschetz thimble. Now, if you're not going to sit at p for all times, but you do want to start at p at time minus infinity, so you better roll away from p in the right direction. If you tried rolling uphill, you wouldn't have been at p at time minus infinity. But you can roll very slowly downhill. And how far you get at time 0 depends on the coefficient of the exponentially small term in the far past. So at time 0, you could be anywhere on this cycle. So the space of values at time 0 of solutions of the flow equation on the semi-infinite line, where you start at p at time minus infinity, gives a Lefschetz thimble, as it's called.
Is it just that curve that you drew or not?
Well, if you solve the problem of finding all solutions on this semi-infinite interval that start at p at time minus infinity, and you take their boundary values at time 0, you'll get a one-dimensional curve that qualitatively will look like this. I gave a...
It's not just the flow line, but not just the line of steepest descent.
Well, I've defined the line of steepest descent, but I've defined it in a way that makes sense in any dimension. What did you mean by the line of steepest descent? I gave a precise definition of what's meant. I gave what I think is the best.
You have several lines in which the detection can be negative, right?
Well, in one dimension, there's a unique direction in which the Hessian is negative. But in n complex dimensions, there would be an n-dimensional subspace in which the Hessian is negative. So falling away from a critical point, you'd have a sum of exponentials with n real coefficients. And the space of solutions would therefore be a copy of Rn. So topologically, the Lefschetz thimble would then be a copy of Rn. So there's a technical assumption required, which is that there's no flow that ends at another critical point. No. Yes. Right. Right. But I believe when we get to infinite dimensions, it's better to have an explicit recipe, which I will use. But you see, anything going down is enough, but it's a little bit vague, because, well, roughly, if you change the metric, after all, the cohomology class of the cycle might jump. Because in a family of metrics, you could, yes, right. So steepest descent is actually too vague. It's not well defined without some additional information, because there are Stokes phenomena. So I gave a specific recipe that only actually works generically. So Morse theory tells us that any cycle in which the integral converges can be expanded in terms of the Lefschetz thimbles with integer coefficients. And moreover, Morse theory gives a recipe to compute these integers. So if you're, after computing the integers, if you're given a gamma, you compute these integers, and then it's straightforward to find the large K asymptotics of the integral, because the asymptotics of the integrals over the gamma p are known. The point is that gamma p was defined so that the integration, what you're integrating, has a unique maximum at the point p. Not really, no. What I'm saying is true anyway. There'd be more critical points if the ambient space had topology. There can be, but nevertheless my statements are true. Such a cycle would be a difference between Lefschetz thimbles. You could have two Lefschetz thimbles that differ by, so if the manifold is topologically trivial, a Lefschetz thimble, as I've defined it, is never compact, but a difference between Lefschetz thimbles might be cohomologous to a compact cycle. And in the situation you asked about, your compact cycle would be actually cohomologous to a linear combination of Lefschetz thimbles. What I said about Moore's theory is true. It proves that the appropriate relative cohomology has the gamma p's as a basis. So you see the integral over, our integral on a gamma p has a simple asymptotics given by the critical points, the value of the exponent at the critical point. So if you have this expansion, it's easy to work out the asymptotics of the integral over any gamma. And what you learn in the case of the analytic continuation of the Bessel function is that it has a qualitative behavior similar to that of the colored-Jones polynomial. The limit as n goes to infinity, with k being a constant plus n, is very different depending on whether k naught is an integer, because the contributions of two Lefschetz thimbles that cancel when k naught is an integer don't cancel when k naught is not an integer. What?
It's kind of a cut you have, because it's not integer.
Well, we avoided cuts because we worked on the W plane where everything was single valued. And then we have this analytic continuation. It's dominated by a sum of Lefschetz thimbles. But it can happen that what is the dominant Lefschetz thimble depends on k. And there can be cancellations possible. When k naught is an integer, two thimbles cancel, but generically they don't cancel. Even if k naught is still real, it spoils the cancellation that occurs if k naught is an integer. In our model problem, we're only doing physically sensible quantum mechanics when k is an integer. So even if it remains real, if it's not an integer, things happen that can't happen in a physically sensible system.
Here you have a sum, but that it is an asymptotic question of
Well, the integral over each gamma p is a well-defined function. So we get an exact formula for the integral over gamma as a linear combination of integrals over Lefschetz thimbles. If we only care about the asymptotics, we only have to look at the asymptotics. But whatever we want to do, this is an exact formula for the integral. So at this stage, I hope it's fairly clear how to study the analytic continuation to non-integer k of the quantum invariance of knots in R3, and also to understand the asymptotic behavior studied in the volume conjecture. We should replace our integral over the space of real connections by an integral over its complexification. And we should replace the usual Chern-Simons integral by a sum of integrals over Lefschetz thimbles. And then in the gauge theory definition of the Jones polynomial, we should replace the usual integral with a sum of integrals over thimbles. The only thing is it's probably not clear that this will actually be useful. That wasn't too clear to me at this stage. So to define the Lefschetz thimbles we want, we have to consider gradient flow in the infinite dimensional space of complex valued connections with the real part of Chern-Simons as a Morse function. Unfortunately, I'm way behind time, so I'm not sure I should have discussed this practice problem, but I thought at least some of you would be familiar with the case of gradient flow on the space of real connections, because it's important in Donaldson and Floor theory of 3 manifolds and 4 manifolds. So if you were studying the space of real connections, and you took Chern-Simons as a Morse function, then you put the obvious Riemannian metric on the space of connections, and you write down the gradient flow equation. So that means you introduce a new time coordinate. So before we were on a 3 manifold, but now we're on a 4 manifold, the 3 manifold times time. So when we flow, we'll consider a time-dependent family of 3-dimensional connections, so it will make 4-dimensional fields. So we're now on a 4 manifold, which is m times time. And we write down the flow equation, dA dt is the gradient of the differential of the Chern-Simons function. And if you do this generically, you're going to get something bad. You won't get a differential equation with nice properties. But there's some magic, which is part of what makes Floor theory work. Actually, this is part of an answer to, well, there's a magic, which is that this is actually a gauge-fixed version of a 4-dimensional equation that's completely elliptic modulo the gauge group. It's the instanton equation, studied by Donaldson and, of course, also by physicists. Not only it's elliptic, but it has full 4-dimensional symmetry. It's naturally defined in any oriented 4 manifold, not necessarily a product of a 3 manifold times R. So these miracles are well known in Donaldson and Floor theory, where they play an important role. The same thing happens in the complex case, or at least a variant of the same thing happens. We do gradient flow on the space of complex connections, with the Morse function now being the real part of Chern-Simons, and we take the obvious Kähler metric on the space of connections. So when I say the same thing happens, what I mean is that the gradient flow equation is essentially an elliptic differential equation with full four-dimensional symmetry. The equation is a kind of four-dimensional cousin of Hitchin's famous equation in 2 dimensions. It's an equation for a pair A and phi, where A is a connection on a G bundle, but now we're in a compact gauge group, so A is a connection on a bundle with compact structure group, and phi is a one form with values in the adjoint bundle. If you're familiar with Hitchin's equation, you know he studied complex connections in real terms, and his equation involved a real connection and a real one form. But in one way of looking at it, you can combine them into a complex connection. There's a version of the same thing here. So our equations, if K is real, are explicitly of this form, and I've written them in a way that has manifest four-dimensional symmetry, but nevertheless, they're flow equations for the three-dimensional connection. Now, something unexpected happens, although I didn't realize this in my first paper. These are actually equations I'd studied before with Kapustin in working on geometric Langlands. So some authors have called them the KW equations. And that'll be useful in a second. But first I'll tell you a couple things we can say without knowing that. So remember, what we're doing is to define a Lefschetz thimble. So a Lefschetz thimble is determined by a critical point in general, of the complexified function. So we take any representation of the fundamental group of our three manifold in the complex Lie group. That gives a complex critical point. We work on a four manifold, which is m times r plus, because in finite dimensional Morse theory, you solve the gradient flow equation on a half line to define a Lefschetz thimble. But now what we're flowing is a connection on a three manifold. So we have to work on a half line times a three manifold. And we study the gradient flow equation, which means the KW equations, for a pair consisting of a connection A and the one form phi, which you can think of as a complex connection on a three manifold. So we flow a three-dimensional connection by solving this four-dimensional equation on a three manifold times a half line. Now, the weight of, if there is a knot, we don't include it in the definition of the thimble. So as actually Tom was talking about before, we just think of the knot as part of the function we'll integrate over the thimble, not part of the definition of the critical point. We could do the other, but I don't want to tell you about the other right now. So we define a Lefschetz thimble that consists of all complex connections that are boundary values of solutions of the KW equations on this four manifold with boundary, and that approach curly A at infinity. And for general M, this construction depends on the choice of a flat connection. And then, if you're interested in the original Chern-Simons function, involving an integral over the space of real connections, what you would have to do is to express the real cycle as a linear combination of Lefschetz thimbles. And there are very interesting questions there that haven't been studied very much, except in a few special cases involving knots in S3. But if we happen, well, that's in the case where the weight is large and we include the knot in defining what we mean by a critical point. But if we're in this situation where a knot is just a function we integrate, so we're just on R3, the fundamental group of R3 is trivial, so any flat connection on R3 is gauge equivalent to the trivial one. And there's only one Lefschetz thimble. And so any integration cycle is a multiple of the standard integration cycle. And therefore, instead of defining the Jones polynomial by integrating over the space of real connections, we can define the Jones polynomial by integration over the unique Lefschetz thimble. I claim that that's actually what's special about knots in R3. And that's why there's a special theory of knots in R3. The integration cycle U that leads to the quantum knot invariance is also equivalent to the Lefschetz thimble associated to the trivial flat connection. So the Jones polynomial can be described now as an integral over the Lefschetz thimble gamma naught, which is the space of solutions of the KW equation on a half space that vanish at infinity, and where curly A is the restriction of A plus I phi to the boundary. And, sorry, this should be curly a here in the definition of the Wilson operator. The function we integrate over the Lefschetz symbol is the exponential of ik Chern-Simons times the trace of the holonomy. But now it's the analytically continued Wilson operator, because we're integrating over a space of complex connections that happen to be boundary values of real ones on this four manifold. So it may sound like a purely formal answer, but there's a reason you can say something about it, which is that my work with Kapustin had involved a twisted version of n equals 4 super-Yang-Mills in 4 dimensions. The twisted theory localizes on the space of solutions of the KW equations. This space, if our connection is required to vanish at infinity, is the Lefschetz symbol we have to integrate over to get the Jones polynomial. So there's a more physical way to say what I just said, which is that the Jones polynomial can be gotten by n equals 4 super-Yang-Mills theory on a half space with a certain boundary condition. I didn't quite say that in my first paper on this. That's not obviously useful, but there's one more step which makes it become useful and also gives a new explanation of why the Jones polynomial is a Laurent polynomial in Q. The step in question is a key step in most work by physicists on n equals 4 super-Yang-Mills. It's called electric-magnetic duality, the four-dimensional analog of mirror symmetry in 2 dimensions. N equals 4 super-Yang-Mills with gauge group G and coupling parameter tau is equivalent to the same theory with gauge group the Langlands or GNO dual group and the coupling parameter minus 1 over tau. But when we use this duality on a four manifold with boundary, we need to know what happens to the boundary conditions under duality. I'll finish in just a minute or two because I'm way over. So people who work on mirror symmetry are familiar with the analogous question in the context of mirror symmetry. The question is, what is the object in the Fukaya category that's mirror to a given coherent sheaf? As understood by physicists, that question has to do with how a boundary condition in a two-dimensional quantum field theory transforms under duality. Here we need to know how a boundary condition in a four-dimensional quantum field theory transforms under duality. In the particular case we need, it's actually quite tricky, but luckily Gayotto and I had answered it a few years ago. It's a somewhat unusual boundary condition, and I said I will say a little about it at the end, but we won't have time. So all I will actually say today is that it's a standard elliptic boundary condition that has the effect of reducing to finite dimensional spaces of solutions of the KW equations, which actually are generically zero-dimensional. So generically, it reduces to finitely many solutions of the KW equations. So in this situation, after making the duality transformation, the moduli space of solutions has expected dimension 0, and we simply count with signs, as in Donaldson theory, the number b sub n of solutions for a given value n of the second Chern class. The boundary conditions depend on the knot k, and that's an interesting story we will not have time for today. And also, I'm not quite sure what was erased, so let's just say that the boundary conditions depend on the knot k. And then the path integral is a sum over all values n of the second Chern class of b sub n, the number of solutions for a given second Chern class, times q to the n. And, well, there's a conjecture here, which is that for sufficiently large absolute value of n, there are no solutions at all. And in this case, this function is a Laurent polynomial in Q, and I expect eventually that conjecture will be proved, and this will exhibit the Jones polynomial as a Laurent polynomial in Q, whose coefficients are the number of solutions of the KW equation with second Chern class n and with the boundary condition I didn't describe. And I think we'll have to stop there. Thank you.